about nuclear energy. In this lesson, you will be able to write a nuclear equation. First, let's do a quick revision for the atom. You know that the atom has two parts, the nucleus and outside the nucleus where the electrons are going around. Now, inside the nucleus, we have two types of particles. We have protons and we have also neutrons, which are neutral inside the nucleus, and the protons are positive. Now, what is the thing that keep the protons and the neutrons inside the nucleus without losing or gaining? The protons and the neutrons are held together by binding energy. This energy keeps them inside the nucleus. Now, if this energy is not enough, so the nucleus will be unstable. So the nucleus, unstable nucleus, is a result for shortage, let's say shortage of energy. The nucleus does not have enough amount of energy, so the nucleus will be unstable. Now, the only way to make the nucleus stable is to lose from the protons and the neutrons, or both of them. You could lose both of them to be stable. Now, when the nucleus lose protons and neutrons, here, protons and neutrons, which is 0 here, charge. Okay, let's leave it without a charge. So here, when the nucleus loses protons or neutrons, it will release one type of energy. So it releases nuclear energy. So this nuclear energy, it's called nuclear energy because it came from the nucleus itself. Now, this type of energy could heat water into steam, or it could generate turbines, or it could provide electricity. Those are the uses for the nuclear energy. The nuclear energy comes only from the splitting of the protons and the neutrons from the atom. Now, if any nucleus lost protons and neutrons, we are talking here about a nucleus itself. So part of the nucleus will be splitted from the nucleus itself. Now, let's see how does it work. Here, if I have, for example, uranium, which is the most famous or popular radioactive atom. Now, from the periodic table, uranium here it has 92 protons, 238 atomic mass. So here I will write the atomic mass on the top, and here I will write the number of protons. Now, we have many atoms of uranium. Now, those atoms are not stable. Those atoms are not stable inside the nucleus. So it will release energy. We will call them radioactive, let's write it like this, radioactive decay, and it will produce also the stable atom. So from the uranium, if it's going through a radioactive decay, it will produce one type from the radioactive decays and one stable atom. This process, we will call it splitting or transmutation. The transmutation happens for the atom when it loses protons, it loses protons and neutrons from the nucleus itself. Now, let's try to write a nuclear equation, but first you have to know the types of the radioactive decays. Now here, let's go down. Types of radioactive decay. Now, the first type is called alpha decay. The second type is beta decay. The third type is gamma decay. The fourth one is called positron. And the fifth one is electron capture. Now those are the types of the radioactive decay. Now let's compare between them. What's the difference between all of them? The difference between those types of radioactive decay will be in the number of protons and neutrons the atom will lose. For example, if I have an atom, some atoms will lose protons and neutrons. Some atoms will lose just protons and some atoms will lose just neutrons. So it depends on the number of protons and neutrons. Here, for example, alpha, symbol of alpha is like this. This is alpha. It has 4 atomic mass and 2 protons. 4 is the atomic mass, which means the number of protons and neutrons inside the alpha. 2 is the proton, so 2 is the charge of alpha. So alpha has 2 positive charge and 4 atomic mass. Now, if you check the periodic table, you will find that helium has 2 and has 4 atomic mass. So alpha could be also helium 4, 2. So you can use alpha or helium. Both of them work. So alpha and helium are the same type of decay. Now beta is like this. This is a symbol of beta. Now it has 0 atomic mass and -1 is the charge for beta. This is the charge of beta, 0, -1. Now gamma, this is the symbol of gamma. It has 0 atomic mass, 0 charge. 0 atomic mass and 0 charge. Positron is the positive electron. It's electron, 0 atomic mass, +1 is the charge. +1 is the charge. Now, here electron capture, it's an electron, -1. So those are the types of the radioactive decays in the nuclear energy. Now, we will use those to write nuclear equation. For example, let's take one question. From here. Now, I will write the question here. Write a nuclear equation for the alpha decay of Pa. Now, first you have to check what is the Pa. From the periodic table, Pa here is it. Now here Pa is protactinium. Protactinium is Pa. Now Pa is 231 atomic mass and 91 is the atomic number. So here I will write Pa 231 and 91 is the atomic mass. Let's check again. Yes. Okay, so 91 is the atomic number of protons. 231 is the atomic mass for Pa. Now the question said that the nuclear equation for alpha decay. So our type here will be alpha decay. Now, alpha is a product. Alpha is a product, so you cannot write it here. So you will draw an arrow. So the reactant is Pa. The first product is alpha. Alpha has 4 and 2. Here you could write He instead of alpha. Okay? Now you have alpha Pa. Now you have another product here. You have here another product. Your product should apply the conservation of mass law. The conservation of mass law is to make sure that all the charges and the masses in the chemical equation are conserved. Masses and charges are conserved. What do you mean by conserved? If you remember, when we used to balance the chemical equation, we checked the number of atoms and the charges. Here you have to check the atomic masses and the charges, meaning 231 the atomic mass for the reactant, so the total atomic masses for the products should equal 231. Now if this one is 231, you took here 4, so the rest will be 221 here, 3, it's 7, 227, and here it's 91, you took 2, so it's 89. So here 227 plus 4, it's 231. So the first one is conserved. The first one, which is the atomic mass, are conserved. Now here 89 plus 2 and 91. 89 plus 2 is 91. So the charges are conserved. Now you have to check the periodic table to find an atom with 89 protons. 89 protons. This is the one who I will look for it. I will use this one to find my atom. Now 89, it goes to, where's 89? It's here. Yes, it's actinium, this one, so it's AC. So here it's AC. Now we used 89 because the periodic table is organized depending on the atomic mass, on the number of protons. Now here 89, 88, and so on. So the periodic table is organized depending or based on the atomic number. Now the atomic mass, if you noticed here, the atomic mass for AC is 227, but the atomic mass here is 227. They have the same atomic mass. In some questions, you will find different atomic mass. Now, if two same atoms have different atomic mass, what do we call them? Isotopes. Isotopes are same atoms with different atomic masses. Why are the atomic masses different? Because they have different number of neutrons. So if they have different number of neutrons, they will have different atomic masses. Now, let's take another question. Now, the question is to write a nuclear equation for beta decay of FeFr francium 22387. So here I will write Fr 223 and 87. Now, it's going by or through beta decay. So, arrow, beta decay is a product. Here I write beta. Beta from our table here is 0 atomic mass and -1 the charge. So here I will write 0, here -1. Now, all the thing I wrote now from the question. The new thing is the new atom. Now, what you have to do now is to check the conservation of mass law. 223, 0. So here it will be 223. Both of them have the same atomic mass, the product and the reactant. So the first one is conserved. The second one is 87, here -1. So I need a number plus -1 to give you 87. So I will write 88. 88 plus -1 is 87, so the charges are conserved. Now I need an atom with 88 protons. I will go here, so it's Ra. Ra, which is radium. So radium is 88. Now, if you noticed here, the atomic mass for radium here is 223, but the atomic mass from the periodic table here is 226. So those are isotopes. Both of them are radium, but the first one is an isotope for the second one. Now this is decay, nuclear beta decay. Let's do another one. Okay, here we have alpha and beta. A nuclear equation for alpha and beta decay. So we have here two types of decays in the same question. For Sm, those numbers, where's Sm? Let's check it. This is samarium, this one, 62-150. Here I have different isotope. I will use this one, which is given in the question. So if the numbers are given in the question, use them. If it's not given, find them from the periodic table. So here, Sm is 149, the atomic mass, and 62 is the protons. Now it's going through alpha and beta decay, so it will produce alpha and beta. Alpha for, let me write it as helium, so you can use to write them both of them are alpha. 4 2 plus beta zero minus 1. Alpha and beta, those from the question. Now the new thing is to write the new atom, which is you have to check the conservation of mass law to find it. Now here I have 149, here I have 40, so here it should be 145. 145 plus 0 plus 4 equal 149, so it's conserved. Now the second number is 62. Here I have 2 plus minus 1, so here I have 1, so I will write 61. 61 minus 1 is 60. 60 plus 2 is 62, so it's conserved. Now find an atom from the periodic table with 61 protons. It's Pm, promethium. Promethium is Pm. So here Pm. Pm. Now 145 is my isotope here from the periodic table. The isotope is 145, so it's the same isotope. Okay, this is alpha and beta. So if you have two decays, it's the same, but you have to count them both. Now let's do another question. Let's do an electron capture question. Write a nuclear equation for an electron capture by mercury 201. Now mercury is Hg. Now the question gave you the isotope. This number, let me write it with another color. Now this number identify the isotope. The isotope here is 201. So the atomic mass is 201. This number is the atomic mass. Now what's the number of protons for Hg? Here, I will check it. Here, Hg is 80. So here I will write 80. Now, electron capture. Now I need from you to know that the electron capture is the only one who will be in the reactants because it's capturing. From the verb capturing, I will write the electron here. Electron minus 1. The electron captured, the electron will be in the reactant. Electron capture, the electron will be in the reactants. So here I'll complete. Now I will just have a new atom because the decay is capturing. So the decay will be in the reactant by the verb capture. So what is your new atom? Here, 201 plus 0. So here it should be 201. So the first one is conserved. The second one is 80 plus minus 1, which is 79. So here it will be 79. 80 plus minus 1, it will be 79. So here it's 79. So the second one is conserved. Now I need to check the periodic table to find an atom with 79 protons. Usually it will be close to your initial atom. So this is Hg, 79 is Au. So here I write the new atom Au, which is gold. Now 201 is the atomic mass for Au. Here it's 190. Sorry, this is OS. Here it's 196. Here it's 196. Here my isotope is 201. So those are different isotopes. Now the nuclear equation always depends on the conservation of mass law. Electron capture in the reactants, the rest will be in the products. Now, why does the nuclear equation happen or the nuclear reaction happen? Because the nucleus is unstable. It lack of energy to keep the protons and the neutrons inside the nucleus together. Next time we will do the missing nuclear equation. We will complete the missing nuclear equation. Assalamu alaikum.